A modern four-season tent, rated for expedition use, tested by professional gear labs, costing upward of $1,000. Set up on the open steppe in a 60-mile-per-hour gale, it fails within hours. The poles flex past their design tolerance. The flat walls catch the wind like sails. Somewhere below -30°C, the fabric turns brittle, the zippers freeze solid, and the structure that promised survival becomes a liability you have to escape. Now picture a different structure. A circular frame of willow lattice, wrapped in felted wool. No metal, no synthetic fabric, no factory tooling of any kind. It has no foundation. It can be taken apart by two people in under an hour and packed onto the backs of camels. And inside it, through the same 60-mile-per-hour gale, through the same -30 air, a family is warm enough to remove their coats. This is the jer, what most of the world calls a yurt. For 800 years, it has been the primary winter shelter of the Mongolian steppe, refined by nomadic herders through a punishing feedback loop, where a bad design decision meant a family froze. And today, structural engineers, cold climate architects, and disaster relief designers are still studying it. Not as folklore. As a working solution to problems modern building science hasn't fully solved. This isn't a tent. It's a piece of design. Every curve, every joint, every layer of felt is there because it survived a test that killed the alternatives. Take it apart, piece by piece, and what you find isn't primitive shelter. You find engineering. Chapter 1. To understand why the jer looks the way it does, you have to understand the environment it was built to defeat. The Mongolian steppe is one of the harshest inhabited landscapes on Earth, not because of any single extreme, but because of the combination. Winter temperatures regularly fall to -30, -40°C. Wind runs across the open grassland with nothing to slow it, gusting past 60 miles per hour for days at a stretch. There is almost no timber. The terrain is flat for hundreds of miles in every direction, which means there is no natural windbreak, no hillside to shelter behind, no forest to blunt the gale before it reaches you. And the people living here weren't settled. They were following herds across that terrain, which meant whatever kept them alive also had to move with them, disassembled and reassembled dozens of times a year. Any one of these constraints, extreme cold, relentless wind, zero timber, constant relocation, would be difficult to design around on its own. Together, they eliminate almost every conventional shelter option. A log structure needs timber that doesn't exist here. A stone structure can't be packed onto a horse. A canvas tent with vertical walls and corners will be shredded by wind that never stops blowing. And anything requiring a poured foundation is useless to a family that needs to be 3 valleys away by next week. The GR is what's left when you solve for all of these constraints simultaneously, using only the materials the steppe itself provides. Wood from the sparse riverbank groves, wool from the herds, and geometry. This is the detail that separates the GR from a tent in the truest sense. A tent is built to be lightweight and temporary, a compromise you accept in exchange for portability. The GR was never a compromise. Nomadic families lived inside one, full-time, for their entire lives, through 50 and 60 winters, generation after generation. The structure had to perform at the level of a permanent home while retaining the portability of camping equipment. That single requirement, permanence and portability occurring in the same object, is what forced every element of the design to be resolved with unusual precision. There was no acceptable version of good enough. A weak point in the frame, a gap in the insulation, a smoke hole that let in more cold than it let out. Any of these killed people. So none of them survived in the design that got passed down. What emerged, after centuries of exactly this kind of brutal iteration, is a structure that modern designers now study for the same reason engineers study bird wings or spider silk. It isn't ornamental, it's optimized. And the optimization starts with the most basic decision of all: the shape. It's worth pausing on just how long that iteration ran for. Historical accounts of round felt dwellings on the Central Asian steppe go back well over 2,000 years, and the specific form we now recognize as the Yurt, the folding lattice wall, the compression-locked roof ring, the layered felt covering, had already stabilized into essentially its modern form by the time of the Mongol Empire in the 13th century. Once a design gets carried across that many generations, in an environment with zero tolerance for failure, you're not looking at tradition for tradition's sake. You're looking at a structure that has already been through more real-world stress testing than almost any building type in human history. Every weak point got found. Every weak point got redesigned or discarded. What survived to become the standard GR is, in a very real sense, the output of the longest field trial any shelter design has ever undergone. Chapter 2. Look at almost any building constructed in the last few centuries, and you'll find corners, rectangular footprints, flat walls meeting at 90 degrees, roofs with edges and eaves. This shape is easy to build with standard materials, easy to furnish, easy to divide into rooms. It is also, in high wind, close to the worst possible shape you could choose. A flat wall facing into wind acts the way a sail acts. The moving air slams directly into the surface, and because the surface can't move, that force has to go somewhere. It pushes against the structure, creates turbulence and pressure differentials along the edges, and concentrates enormous stress at the corners, which are the weakest points in almost any frame. This is why storm damage disproportionately starts at corners, at eaves, at the places where flat planes meet. The building isn't failing randomly. It's failing exactly where the geometry made failure most likely. The GR has none of these features. Its footprint is a circle, and its wall is a continuous curved surface with no flat faces and no corners at all. When wind meets a curved wall, it doesn't stop and push. It gets deflected along the surface, smoothly redirected around the structure, and rejoins on the far side. The wall isn't resisting the wind through brute strength. It's avoiding the confrontation altogether, letting the air flow past the way a river flows around a smooth stone rather than crashing into it. There's no flat face to catch the gust, and no corner to concentrate the stress. The load gets distributed evenly around the entire circumference instead of piling up at a handful of vulnerable points. This is precisely the principle behind aerodynamic building design today. Round grain silos, wind turbine towers, curved facade high-rises in typhoon and hurricane zones. All of them use the same logic the GR's builders arrived at empirically, centuries before anyone had the vocabulary of fluid dynamics to explain why it worked. Modern engineers run wind tunnel simulations and computational fluid dynamics models to arrive at a conclusion the steppe already knew. Corners are liabilities. Curves are efficient. Cold climate researchers studying wind loading on remote structures have pointed to circular Yurt-style geometry as a reference case, precisely because it performs so well without any of the active engineering. No reinforced steel corners, no wind bracing, no complex foundation anchoring that a rectangular structure of comparable size would require. There's a second advantage buried in the circle that's easy to miss. A circular footprint has the smallest possible surface area for a given interior volume. That matters enormously for heat retention, because heat escapes through surface area, through walls, through roof, through every square foot of boundary between warm inside and cold outside. Shrink the surface area relative to the space you're heating, and you shrink the rate at which that space bleeds warmth into the night. The GR's circular shape isn't just about surviving wind, it's simultaneously minimizing the thermal loss the structure has to fight in the first place. One geometric decision, two separate engineering problems solved at once. But a curved wall needs a way to actually stand up without corners to brace it, without a rigid rectangular frame locking everything into place. And that's where the GR's second major innovation comes in. The part of the design that looks, at first glance, almost too simple to work. Chapter 3. Take the covering off a GR, and what's left is a skeleton unlike almost anything in traditional architecture. A wall built entirely from a folding wooden lattice, holding a roof made of compression alone, with no nails, no metal fasteners, and no rigid joints anywhere in the frame. The wall is called the khana, sections of thin willow or poplar poles, crisscrossed and pinned at each intersection with a leather or rawhide joint that allows rotation. In storage or in transit, a khana section collapses flat, like an accordion, folding down into a compact bundle that a single person can carry. Set up, the same section expands outward, and the crisscrossed poles lock into a rigid, self-supporting cylinder, purely through the geometry of the X pattern and the tension of the joints. Several khana sections link together end to end to form the full circular wall, and the shape itself, a continuous curve with the ends tied back into a closed loop, gives the structure most of its strength. There's no need for corner posts or diagonal bracing, because a closed circle under even tension is already about as structurally efficient a shape as you can build. This is a piece of design that modern engineers recognize immediately, because it's the same principle behind scissor lift mechanisms and certain deployable space structures. A lattice that trades between a compact, collapsed state and a rigid, expanded state using nothing but the geometry of its own joints. The GR's builders arrived at this solution using willow poles and leather lashings. It still functions on exactly the same mechanical principle used in expandable architecture today. The roof takes the engineering a step further. Radiating poles called uni run from the top of the khana wall inward and upward to a central wooden ring, the toono, set at the peak of the structure. Every one of those roof poles slots into a socket carved into the toono, and here is the detail that architects find genuinely remarkable. Nothing holds those poles in place except compression. There is no glue, no nail, no metal bracket locking each pole into its socket. The weight of the poles themselves, angled inward and pressing against the ring from every direction simultaneously, creates a self-locking system. Push down on the ring, and the poles press harder into their sockets. Try to remove one pole without releasing the others, and the whole assembly resists you because the load is shared and balanced across the entire ring. It's the same structural principle behind a Roman masonry arch or a stone dome. Compression forces distributed through a ring, converting downward weight into lateral, self-stabilizing pressure. Except here, it's executed with wood, rope tension, and no mortar of any kind. The result is a roof and wall system that can support significant snow load, resist heavy wind, and remain standing for years, and yet can be fully disassembled by two people in under an hour, with every component light enough to load onto a single pack animal, rigid enough to be permanent. light enough to be nomadic. Those two requirements should be in direct tension with each other in almost any other structural system. The khana and toono frame resolves that tension using nothing but the shape of the joints and the physics of compression. Once you have a frame that can stand up to wind and snow while folding flat for transport, you still need to solve the problem that actually keeps people alive through a Mongolian winter, retaining heat. That job falls entirely to what covers the frame. Chapter 4. A wooden lattice, however cleverly engineered, is not a thermal barrier. Wind and cold pass straight through an open frame. What turns the GR from a skeleton into a livable shelter is the layer wrapped around it. Felt, made from pressed sheep's wool. And it's here that the GR's design solves a second engineering problem as elegantly as it solved the structural one. Felt isn't woven. Woven textiles, no matter how tightly constructed, have a regular grid structure with gaps between the threads. Gaps that air can move through, carrying heat away with it. Felt is made by working raw wool fibers with moisture, heat, and repeated pressure until the microscopic scales on each individual fiber lock together, tangling into a dense, disordered mat with no regular structure at all. That randomness is the entire point. A tangled mat of fiber traps countless tiny pockets of still air throughout its thickness, and still air is one of the most effective insulators available in nature. It's the same basic mechanism behind modern fiberglass batting and synthetic insulation, just executed in wool instead of spun glass or polyester fiber. A GR's walls and roof are typically wrapped in 2 to 4 layers of this felt, each layer several centimeters thick, laid to overlap the seams of the layer beneath it. Tested against modern insulation standards, multiple layers of properly pressed wool felt land in a comparable R-value range to standard fiberglass batting used in contemporary residential construction. A genuinely striking result for a material made with no industrial processing, using tools that predate the loom. Over the felt goes an outer layer of canvas or tightly woven cloth. And this is where the GR reveals a second layer of engineering that has nothing to do with keeping heat in and everything to do with managing heat from the sun. In summer, the outer covering is left in its natural pale, undyed state. Light-colored fabric that reflects a large share of incoming solar radiation rather than absorbing it, keeping the interior from overheating during long steppe days. In winter, families add an additional layer of darker felt or fabric beneath or over the existing covering, specifically to absorb more solar radiation and add passive heat gain on clear, sunlit days. The same structure, seasonally reconfigured, actively manages solar exposure in 2 opposite directions, depending on what the season demands. This is the exact strategy modern passive solar design refers to as adjustable albedo, changing a surface's reflectivity to control how much solar energy it absorbs. Deployed here centuries before the term existed, using nothing more than which side of the felt gets flipped outward. The measured results of this combined system are substantial. Field recordings from GRs in use through Mongolian winters have documented interior to exterior temperature differentials exceeding 60 degrees Celsius, sustained with nothing more than a small stove, burning a modest, steady fuel load. That is not a marginal improvement over exposure. It is the difference between a survivable interior and a lethal one, achieved through wool, geometry, and the physics of trapped air. No synthetic materials, no powered heating system, no sealed mechanical ventilation. Frame and felt together solve wind resistance and heat retention. But a shelter isn't finished once it stands up and holds warmth. It still needs to breathe, to let in light, and to manage the 2 forces, smoke rising up and cold air pressing in, that define daily life inside it. That's the layer of design hiding in the details. Chapter 5. Step back and look at the GR as a complete system, and the smallest details turn out to be doing some of the most sophisticated work. Start at the top, with the toono. The same wooden ring that locks the roof poles together through compression is also the structure's smoke hole, its skylight, and, in traditional use, a rudimentary solar calendar. Positioned at the exact center of the roof, it vents smoke from the central hearth directly upward and out, using the same basic stack effect principle that drives a chimney. Warm air rises, and rising air pulls fresh air in behind it through the gaps at the base of the wall, creating continuous, low-effort ventilation with no moving parts. During the day, that same opening admits a column of natural light directly into the center of an otherwise enclosed space, and because the sun's position in the sky shifts predictably across the seasons, the angle and position of light, falling through the toono changes in a way that traditional users could read. The ring doubling as a passive built-in method for tracking the progression toward the winter and summer solstices, entirely without instruments. The toono can also be closed, using a felt flap on a cord that's pulled shut during storms or the coldest overnight hours, sealing the primary heat loss point of the entire structure on demand. Open for ventilation and light. Closed for maximum heat retention. A single component managing 3 separate functions: smoke exhaust, daylighting, and seasonal tracking, with one flap of felt as the only moving part. Then there's the door, and its placement is not incidental. GR doors are built low, forcing anyone entering to duck, and they are oriented to face south, without exception, across the traditional design. The low height matters because cold air is denser than warm air and sinks, pooling near the ground. A low door sits within that cold layer, which means opening it briefly lets in a comparatively thin slice of cold air, rather than a full-height gust straight into the warm upper zone where people actually sit and sleep. The southern orientation matters for a different reason entirely. In the northern hemisphere, south-facing openings receive the most direct and the longest exposure to sunlight throughout the day, especially in winter when the sun sits low on the horizon. A south-facing door doesn't just admit light. Placed correctly, it can catch direct sun at a low, warming angle during the exact months when passive heat gain matters most. 2 design decisions, one about the physics of density and one about the geometry of the sun's path, both baked into where a single door gets placed. The cumulative effect of all of this, the circular shape deflecting wind, the compression-locked frame carrying structural load without fasteners, the felt trapping still air at a modern comparable R value, the seasonally reversible solar gain, the smoke hole managing ventilation and light and season tracking simultaneously, the low south-facing door is a structure where nothing is decorative. Every visible feature is load-bearing in some sense, either structurally, thermally, or functionally. That is precisely why modern designers keep returning to it. Field hospitals deployed to cold climate disaster and conflict zones have adopted Yurt-derived geometry specifically because it can be erected quickly without heavy equipment, resists wind loading without a poured foundation, and retains heat far more efficiently per unit of fuel than a standard rectangular tent structure. Arctic and high-altitude research stations, where every kilogram of construction material has to be transported at enormous cost, have looked at the GR's strength-to-weight ratio as a genuine reference point. A structure that achieves permanence-level performance using a fraction of the material a conventional building would require. And the broader off-grid and passive housing movement, focused on building shelter that performs well with minimal or no mechanical heating and cooling, treats the GR less as historical curiosity and more as a proof of concept. A fully passive system, with no electricity and no powered climate control of any kind, that has been keeping people alive through some of the harshest winters on the planet for 8 centuries running. It's a strange kind of validation, watching contemporary design teams run computational wind load simulations and thermal modeling, software on a structure whose original designers never wrote anything down, never had access to a single calculation, and worked entirely by observing what killed people and what didn't. The gap between those two design processes, centuries of empirical trial and error versus a laptop running finite element analysis, keeps landing on the same conclusions. That's not a coincidence. It's a sign that both processes are converging on the same underlying physics, just by radically different routes. One used generations of Mongolian winters as its test lab. The other uses software. The answers, again and again, match.